Now let's review a little bit about what we know about these normal probability curves. The shape is a bell shape. Also, the mean is the center value associated with the peak, as opposed to sometimes we saw curves a long time ago with previous modules. They weren't really bell shaped. They were kind of skewed right or skewed left. These bins kind of went, and then they went smaller and smaller over here. Sometimes when they're skewed right or skewed left, the mean won't be the highest peak. It'll be somewhere between. But as long as it's a bell-shaped curve, the peak of it should be the mean as a center value. The standard deviation measures the spread about the mean. The standard deviation affects the shape of the normal curve. The normal curve is always bell-shaped, but it can be short and squat or tall and skinny, depending on the value of the standard deviation. That's kind of what we talked about on the previous page. The area under a normal probability curve is 1. Normal probability curves also have another important feature. The area under the curve associated with values within 1 standard deviation of the mean is always 0.68. This is true for every normal probability curve, regardless of the value of the mean or standard deviation. So I guess this 0.68 is just a constant value that is associated with these things. I said that's always the area under the curve associated with values within 1 standard deviation of the mean. So we'll look more at that below, but just think of it kind of like pi. If you remember from algebra or pre-calculus or whatever class, pi is 3.14, dot, on and on and on and on. But it's a constant that has to do with circles and the circumference versus the diameter and stuff. So that's kind of similar to this. We just happen to always see this guy. This is the area under the curve right where the mean is between the 2 standard deviations. 1 standard deviation left of the mean and 1 standard deviation right of the mean. So we'll look at that. Here's a picture here that kind of describes it a lot better than I could verbally. Let's see, example, 1 standard deviation on each side of the mean. So let's start with the quantitative variable x that has a normal probability distribution with mean 10, just for a nice round number, and standard deviation 2. Let's practice our new notations. Okay, mu is 10. That's our mean. Just because we're looking at a curve here that we use, or someone found by doing some mathematical model or calculations, it wasn't the mean of a bunch of data values. The normal probability curve for x is shown below. And they said the standard deviation is 2. Okay, so 10 is the middle, the highest, the peak. 2 data points left of that, 2 data points right of that. If you make a line down, the area beneath the curve between those 2 data points, 8 and 12, which is the mean minus the standard deviation, in other words, 10 minus 2 in this case, all the way to the mean plus the standard deviation, so 10 plus 2. And that area beneath those will always be 0.68. The remainder of the area will be here and here. And we know that the blue area would be, just for fun, just to make sure we're really understanding it, blue area. It's left on the left and the right. If I take the green middle area away, because the whole area under the curve, they said, is always 1. The blue area would be 1 minus 0.68, which is 0.32. Yeah, just for fun. So I don't know. And then I guess the blue areas are each half of 0.32. So each of them is going to be 0.16. Interesting. Anyway, okay. Let's move down a little bit here. Okay. We got that. We can see the curve. Okay, sounds good. As expected, the mean 10 is located at the center of the normal curve. The other 2 arrows point to values a distance of 1 standard deviation on each side of the mean. The point that is 1 standard deviation less than the mean is represented by mean mu minus the standard deviation sigma. We already kind of talked about this. It's at 8. Yeah, okay. And then the other one's at 12 because that's the mean 10 plus the standard deviation 2. You will notice that we have indicated that the area of the green region is 0.68, so we can say that the probability of x being between 8 and 12 equals 0.68. Or using probability notation, we could write the probability of x being between 8 and 10 is 0.68. Okay, now let's move down a little bit. Oops. Now we're going to look at an example with baby birth weights. Okay. Baby birth weights have a normal probability distribution with mean mu is 3,500 grams and standard deviation is sigma equals 600 grams. What is the probability that a baby's birth weight is within 1 standard deviation of the mean birth weight? The answer, the probability is 0.68. Because if you draw the curve, you want it to be, here's mu, they want it to be within 1 standard deviation of mu, but that was just exactly what we had in that curve above, mu minus sigma. It doesn't really matter the values below, but if you say you want it to be within either a higher 1 standard deviation than the mean or lower, that calculates the area from here to here beneath the curve, when they said was 2.68. To be more precise, there is a 68% chance that a randomly selected baby will weigh between either, mu minus sigma, which is 2,900 grams if you do the math, 3,500 minus 600, and 4,100 grams, which is the mean plus sigma. 3,500 plus 600 is 4,100 at birth. So now we'll summarize. For any normal any normal probability curve, the center area within 1 standard deviation of the mean equals 0.68. No matter what we're talking about, no matter what the variables represent, that's what it's going to be for these probability curves. This is the same as saying 68% of the time we will expect x to have a value within 1 standard deviation of the mean. And then symbolically, you can write that as this formula. Probability of x being between mu minus sigma and mu plus sigma is 0.68 or 68%. Are you surprised by these statements? After all, we have seen that the standard deviation affects the shape of the normal curve. The normal curve is always bell-shaped, but sometimes it's short and squat, sometimes it's tall and skinny. Regardless, the area under the normal probability curve is always 1. In other words, 100%. In addition, the values within 1 standard deviation of the mean occur 68% of the time. We examine this idea further in the next example. Okay, let's move down. All right, now we'll talk about inflection points. Inflection points. So look at the red arrows pointing at the normal curve in the following figure. At these points, the curve changes the direction of its bend and goes from bending upward to bending downward, or vice versa. A point like this on a curve is called an inflection point. Every normal curve has inflection points at exactly 1 standard deviation on each side of the mean. And if you ever take calculus for your major, for whatever, you'll see that inflection points are part of calculus as well. Yeah, you notice in the middle of this standard deviation curve, you're kind of curving downward, but once you get to a certain place, now you're not curving downward. It's not like a upside down cup. Now it's like a right side up cup. It'll start kind of curving inward, if that makes any sense. You can hold water in that one. This one, the water's going to fall out. I don't know. Is that a weird way to think of it? Yeah, kind of makes sense. This looks like a downward slope sort of, and then this looks like an upward slope. There's a certain point where it changes from sloping kind of downward to upward. The diagram shows what we mean by concave down and concave up. That's another way to say it. That's more the precise way. So this portion here is concave down. Like I said, it's kind of like an upside down cup, imagine. It can't hold any water or any liquid, but a right side up cup, this is half of it, I guess, a cup, and here's another one that can hold something in it. That's concave up as opposed to concave down, where what the middle looks like. Okay. Now we're going to look at an applet. With the following applet, you can look at a variety of normal curves. Use the slider to change the standard deviation to get different normal curves. Observe that the 2 properties we discussed in the examples remain true for any standard deviation you select. The probability that a value is within 1 standard deviation of the mean is 68%, or 0.68. The x values of the inflection points correspond to 1 standard deviation above and below the mean. So yeah, sometimes it's hard to tell with a certain graph, but these, where it changes from purple to whatever that is, mustard yellow, is an inflection point, and it happens to be, like they said, 1 standard deviation above and below the mean, mu plus sigma or mu minus sigma. Oops, what am I doing? So standard deviation is 4 in this case, but what if I make it smaller? So you kind of notice as I make standard deviation smaller, I'm just moving this little cursor guy. It's still it's hard to tell, but it still looks like the inflection point does occur at that place where the color changes from yellowish, brownish to purplish. So no matter what you make the standard deviation, it doesn't matter. First of all, the area under this curve is always 1 no matter what. If I make it a narrow curve because standard deviation is small, it's compensating by getting taller. If I make standard deviation larger, which makes it wider, it's getting shorter, so that the area always stays 1. And also, no matter what, the inflection point stays at sigma plus mu and sigma or mu minus sigma, those inflection points.